Welcome. So we continue our lectures on long-term potentiation and long-term depression and implementation of those in models of neurons. So as we discussed in the previous lecture, we are taking only rates as responses in this case and not really considering timing of spikes in general, and with that we are building towards more realistic models if possible with biological basis. So the first two rules that we have discussed are the correlation based rules and the covariance based rules. So interestingly, as you saw, let us just remind ourselves, we have this rate of change of W with a time constant. This is equal to V u, and when we average over multiple input patterns, then this translates to Q into W, where Q is the correlation matrix. And similarly, in the covariance rule, there are two of them, tau W dW dt is equal to V minus theta V, which we will replace with the average activity of V times u, or is equal to V times u minus theta u, where the theta u again will be taken as the average of u, and these turn out to be, when we average over multiple input patterns u, we get the rule that is the covariance rule, which is CW. So what are the problems with these two? Both of these are unstable, that is, the weights sort of diverge. Another problem with the correlation rule is that there is no LTD here, because it is continuously increasing, because V and U are both positive, and so that is why the threshold is introduced in the covariance rule, and it is made the covariance by making it the average of the input activity for the input threshold and average of the output activity for the output threshold, and here we can get LTD. But now if you observe in this particular case, where in the covariance rule we have tau W dW dt, the original form, where we have V minus theta V, which is the average of V times u. So in this case, if we set V to be 0, that is, there is no output activity no matter what the input activity is. So then that becomes a problem, in the sense that you still get LTD, although it is seemingly correct in the sense that the input activity is not driving any output activity, and so the synapse will depress and die. But evidence shows, experimental evidence shows, that you require some postsynaptic activity in order to get long term depressions, LTD. So here momentarily V is 0, and we would still get depression or LTD, which is not correct in the sense that it is not supported with experimental evidence. And similarly, we need both pre and postsynaptic activity to observe LTD, and so here it is, in the other case, we have V times u minus average of u. So again here, if we set u to be 0, then again we see that there is still LTD without any presynaptic activity. Now of course, if u is always 0, that is fine, but when there are periods when u is 0 and you still keep on getting LTD due to postsynaptic spiking, that is not supported by evidence. So we require both pre and postsynaptic activity. So the problem of not LTD not being there is removed by introducing a threshold from the Hebb's correlation based rule. And by introducing a threshold, the problem that we are getting is that there is LTD without presynaptic or postsynaptic activity, depending on which version of the model we are using. And that led to probably the most realistic such rate based plasticity models, which is the Bienenstock, Cooper and Munro learning rule, or the BCM rule. So, in this case, what we see is that we set the dw dt with this tau w as the time constant, and that is equal to our v u times v minus theta v. So, here the rule is very similar to the previous one, but if in this case, if let us say our v is 0, then our weights are not updated, because it is also proportional to v itself, and so our w remains constant. So, this way we remove the requirement we remove the limitation of the covariance rule, where we are using v explicitly, another v explicitly, to control for that lack of postsynaptic activity leading to depression, because in such scenarios w becomes a constant wherever it was. So, in terms of the stability, if we look at this particular rule, then if we consider again as we did for our norm w square and how it changes with time, then let us also multiply that with the tau w, and so that becomes our twice v tau w, and in that case we multiply it with w and dw dt, and so now we replace dw dt with the term above, and what we have is twice tau w times w times v u times v minus theta v. So, for simplicity we will remove the tau w, because it is simply a scalar, and so what we have on the right hand side, that is the derivative of the norm times the tau w, is w times or rather the tau w is actually removed, because with the tau w dw dt is the term that we have. I am sorry. So, we have w times v times u times v minus theta v. So, now remember that we have our v equals w dot product with u, which is, if we take, because v is a constant, we take it out, this is w times u, and we simply get here twice v square, and we have v minus theta v, and this theta v we will again take it as average of v, that is, if the activity is above the overall average, then we will have potentiation, and if the activity is below the overall average, that would lead to depression. Remember, this tau w is extremely the time constant are over very large time scales, that is, we require a number of such events to actually see changes in w. So, w changes at a very long time scale, that is, it is extremely slow. So, here we put in this average of V, and so now if we do the time average of or multiple patterns of this case, then we will get the average change of the norm of W. And so, if we look at this equation, what we have is average of, so basically the dW square dt turns out to be average, on average turns out to be average of twice V square V minus V. So, in this case, if we take one V inside, then we have, and the 2 can come out, we have V times V square minus V times average of V and average of that. Now, we know that V is greater than 0. So, let us say V has a minimum value, let us some particular V naught, and so we can replace this V by this V naught and can say that this is going to be larger than that, since V is positive. And so, ultimately our the norm squared derivative depends on the average of V square minus V and average of V. So, this average, if we take the average in, is essentially V square minus V times V, and what we have here is V square minus V squared, which is simply the variance of V. So, since the variance is positive, variance of V, that is of the output activity V square, this is always greater than equal to 0 unless our V is constant. Then what we are seeing is again that the norm of the weight, that is the length, in this case let us say Euclidean norm, then length of the weight keeps on increasing. So, this being greater than 0, this is increasing, and hence even the BCM learning rule in this form is unstable. So, this, how do we get rid of this instability? And again we have to remember that we have to base our changes and equations and whatever we derive based on realistic biological systems, based on observations that we see. So, what they actually did, I mean there are multiple versions of this rule, the BCM rule. So, here we have again V u times V minus theta V, and what the rule adds on to this is that let there be a sliding threshold or a changing threshold. So, in other words, we introduced d theta v dt with a time constant theta, which is v square minus theta v. So, essentially what are we doing here? So, because having the theta v fixed leads to instability, meaning that our length of the weight keeps on increasing unbounded, or all of them, I mean all the elements of the W reach some saturation value in terms of the plasticity, even though there is LTD in there. I mean LTD and LTP both are at play, still the norm keeps on increasing. So, what this does is, by introducing this theta v dynamics or the sliding threshold, you make the threshold change dynamically such that as the output activity increases, that is gradually as the output activity increases, our theta v is made to go higher and higher. So, this time constant of tau theta is such that it is faster than the time constant of this tau w, in the sense that over a period of time in which the w is changing, that is, we are playing multiple patterns and w is changing very slowly, within this period theta v is changing much faster, and when w is getting finally updated or increased, our theta v has gone over multiple values depending on what the output activity has been in the over time. So, as we see, so if if we have a sort of a fixed output activity going on, then theta v would approach this v square value, which is very large. So, what are we then trying to do is basically, so if let us say we have a number of synapses or inputs, and so we have W1, W2 up to WNB. If we say that NB is the number of synapses that we have, or the number of inputs that we have onto the postsynaptic neuron, then if let us say some of the weights increase and make the output activity large. Let us say, so you are starting out with a flat set of weights, and based on the input activity some of the weights are increased and the V became larger, the output activity became larger, and so the threshold is set to a larger value. With the larger value of the threshold, what happens is that it gets more and more difficult for the system to get potentiation, and in fact it leads to depression because of the V minus theta V term here. And so it gets more difficult for every synapse, in fact the weaker, especially the weaker synapses, to increase themselves. And so this leads to competition between the synapses. So that is, those outputs that those inputs that are causing stronger outputs are weighted more, and the other sort of synaptic weights are dying down gradually. So here we do not have the problem of an unbounded growth of W, because inherently we are putting in a threshold, or rather the inherent properties of these equations is putting in a threshold based on the output activity, that is stopping the system from growing out of hand, or for the weights to diverge. So because our theta v will be going towards v square, the more activity we get, more input activity we get, it is more likely that our v minus theta v is negative, and because our v square, I mean v is positive, v square is very large, and so it will take a while for the system to get potentiation based on the inputs, and it is likely that the largest inputs, the largest the weights that have increased the largest, they might be able to drive it further forward. So this competition that is introduced between the synapses actually is important here, and so which was missing in all the earlier models. So here ultimately in the BCM rule, what we have is that we have both LTP and LTD based on both input and output activity. We remove the problem of zero activity based depression. So this is removed. We have stability in growth of synaptic weights, which is an important factor which was not there in the earlier models. And on top of this, we are introducing competition among the synapses. So, so I was saying that BCM rule comes the closest possible probably in terms of biological learning in with these kind of rate models in neurons, because that in fact the more large the output activity turns out to be, the more difficult it gets for the neuron to increase its responses or increase the synaptic inputs. That is an observation which on the long time scale is also called homeostatic plasticity, but the mechanisms of that are slightly different than what the way this has been presented in the BCM rule. So, there are ways in which that or there are biological mechanisms by which actually there is scaling of the synapses. So, here we are introducing a constraint on the increase in the weights based on the output activity. So, there are learning rules that are based on direct constraints on the weights, and they are more similar to the homeostatic plasticity kind of rules, where we observe some maintenance of activity at an average level, and that requires direct constraints on the weights. So, we will be discussing those direct constraint based models or implementation of synaptic plasticity in our subsequent lectures. Thank you.